Has anyone here actually deployed a robot that runs 24/7 for more than a year without a human babysitter? The short answer is no. The long answer explains why your theoretical reliability models are lying to you. By the end of this video, you will understand exactly how mechanical wear and power cycling force human intervention, shifting the role of the babysitter from software supervisor to hardware lifeline. We live in an era where software frameworks promise a future of configure once and forget forever. Take the framework called Aeon, for instance. It markets itself as the most autonomous agent framework available, explicitly claiming no approval loops are necessary for digital workforces. This creates a compelling narrative where digital logic can self-heal from hallucinations and loops indefinitely. It sounds like the holy grail of automation. But there is a critical disconnect between the digital realm and the physical world. When you move from code to actuators, the laws of physics introduce failure modes that no amount of clever logic can solve. The prevailing narrative conflates software orchestration failures with physical reality. In the digital world, a hallucination is a temporary glitch. An agent can detect the error, backtrack, and try again. But in the physical world, failure is often cumulative and irreversible. The primary barrier to year-long unattended operation is not computational logic. It is mechanical wear, dust contamination, and the fatigue induced by daily power cycles. These factors degrade hardware reliability far faster than any software can self-heal. Consider the concept of mean time between failures, or MTBF. This is a standard metric used in engineering to predict reliability. It suggests that if a component has a high MTBF, it should run for years without issue. However, these theoretical models fail to account for the cumulative damage of daily on and off cycles. Every time you power a robot on, the thermal expansion and contraction of materials creates microscopic stress. Every time an actuator engages, friction removes material from gears and bearings. Over 12 months, these micro-events compound into macro failures that a software agent cannot fix. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This gap between deterministic self-orchestration and actual year-long autonomy is often bridged by an architectural decision to accept higher maintenance frequency. Engineering teams frequently mistake the absence of approval loops for true autonomy. They see that the robot does not need a human to approve every decision, so they declare it autonomous. But without physical redundancy for wear and tear, the system inevitably degrades to a state requiring manual intervention. The robot is still running, but it is running on borrowed time until a sensor drifts out of calibration or a motor burns out. There is a hidden layer of human intervention in deployments that claim to be unattended. Practitioners note that while digital agents can recover from logic errors, physical robots face irreversible degradation. The human role has simply shifted. It is no longer about supervising the logic or watching for hallucinations. It is about managing physical decay. You are now the hardware lifeline, the person who must physically replace a worn gear or clean a contaminated lens before the robot stops working entirely. Look at the tools explicitly named babysitter, such as the AI project. These tools mandate human approval at decision breakpoints. This proves that human oversight is currently an architectural necessity for complex agentic workflows rather than an optional luxury. The existence of such tools highlights the current state of the industry. We do not yet have systems that can handle the unpredictability of the real world for extended periods without intervention. The gap between the promise of autonomy and the reality of deployment is defined by the hardware itself. The failure rate drivers in real-world deployments are not software bugs. They are non-software mechanical wear, contamination, and power cycle-induced component fatigue. These factors account for the vast majority of failures that force a human to step in. A robot might have a software uptime of 99.9%, but if the mechanical components fail due to dust or thermal stress, the entire system stops. This creates a critical knowledge gap in the industry. There is no public data on physical robots sustaining 24/7 operation for 12 months or more without maintenance. We often assume that because a robot can run for a week in a controlled lab, it can run for a year in a factory. But the lab environment is sterile. It lacks the dust, the vibration, and the temperature fluctuations of a real-world deployment. The unpredictability of the environment accelerates wear in ways that theoretical models do not capture. This means the autonomy we see in demonstrations is bounded by hardware lifespan and environmental unpredictability. The babysitter is not a sign of failure. It is a necessary component of the system architecture for the foreseeable future. So when you see a robot that claims to be fully autonomous, ask yourself what happens when the battery degrades or the sensor gets dirty. The answer is usually that it stops. The system requires a human to reset it, clean it, or replace a part. This is not a software limitation, it is a physical limitation. Until we develop hardware with industrial-grade redundancy that can withstand continuous thermal and vibration stress, the human babysitter will remain essential. The role has changed, but it has not disappeared. We are managing physical decay, not just software logic. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.